Hello, my name is Amari Hitton, and thank you for watching my Lab 4 presentation entitled Oscillating Spring Motion. The objective of this lab is to observe a spring mass system in motion. We will then use this observation data to create a computer model of the observed motion and compare the two models. Following the experiment, we seek to answer two questions. Firstly, is the energy principle satisfied? And secondly, how do the oscillation periods calculated using the x or y value coordinates compare? These questions are particularly valuable because they help to better understand the components necessary to both observe and predict complex spring motion. Such predictions would be of great value in reference to predicting the safety constraints necessary to perform extreme sporting events such as the rope swinging video accompanying this lab. We'll start by addressing what's included in our system. The energy principle equation depends very strongly on the assignment of the system versus the surroundings. For our purpose, we distinguish the mass block as our system and the Earth as our surroundings. In this way, we are better able to distinguish what forces are acting on our system. We know, for example, that the spring acts as an agent to the mass block system and exhibits a spring force onto the block. Similarly, we know that the Earth acts as an agent exhibiting a gravity force on the block as well. Using the information derived from this distinguishment, we can utilize several basic concepts to better understand the nature of the oscillating spring motion and answer the question, is the energy principle satisfied? The law of conservation of energy states that the total energy within an isolated system remains constant and is said to be conserved over time. If indeed this principle is satisfied, we should observe a constant total energy reflected in the oscillations of the components of the total energy, the spring potential energy, gravitational potential energy, and kinetic energies. In order to predict the motion of the oscillating mass, we will utilize a derivation of Newton's second law in order to predict the velocity and updated position of the mass at any given moment. The equation for this new velocity is equal to the initial velocity plus the net force over the mass times the change in time. Despite knowing the updated position and velocity, there are still a few values necessary to compute the total energies. Firstly, we will need the spring constant, found using the equation 4 times pi squared times the mass over the time squared. Here, time is found by taking the average time taken to complete 3 oscillation periods. This can be done using the x and y components, as both are of importance to this lab and answering the question initially asked. For the x values, we compute the spring constant to be 6.3348, while for the y values, we compute this period of time to be 7.48417, the number that I will utilize for the rest of my calculations. Next, we compute the relaxed length of the spring, done using the magnitude of L minus the mass times the acceleration due to gravity over the k constant that we just computed. The resulting answer is 0.17361 meters. In order for the model to calculate these energies, it must also be able to predict the motion of the mass. This is done iteratively using Newton's second law, F is equal to ma, and its derivation to calculate the velocity and new position. One of the components of the final velocity equation relies on the net force, which is derived by adding the spring force and the force of gravity. The model relies on the input of a CSV file containing the coordinates of the observed motion. We obtain this file by placing a video of the observed motion into our software tracker, then putting these points on a separate spreadsheet, which is then converted into the necessary CSV file. These are the necessary x and y coordinates plotted here. This brings us to our initial question. Does this satisfy the energy principle? The answer is yes. Looking at this graph, we see that the total energy, represented in yellow, remains constant throughout the experiment, as it is the sum of the spring potential, gravitational potential, and kinetic energies. All of these energies oscillate back and forth between positive and negative values, always summing to 0. Finally, we are able to compare the observed model with the computational model created with the period using the y-component period oscillations. Earlier, we wanted to compare the two period oscillation time values, and from the experiment, I was able to deduce that the y-component value was more accurate as it models the motion of a spring, while the x-component models the motion of a pendulum. When we compare the position of the computer model with the x-component derived k constant and relaxed length, we receive a model that does not look like our observed model. One final note. You may notice that the red line, the observed real-world model, doesn't directly match the computational model shown in blue. This is because at time t equals 0, the mass was in the process of being released from rest. Because of this frame choice, the moment in question may not have been the initial velocity of 0 as stated in the initial parameters of the computer model. In conclusion, we can state that yes, the energy principle was satisfied, and the use of the y-component period oscillations was a more representative model of motion than the x-component period oscillations, who more accurately resemble pendulum motion. Thank you for watching.